Imagine this. You visit a planet for 3 hours, sure, and when you return, 23 years have passed on Earth.
Waited years.
Sounds like sci-fi, right? But here's the kicker. This is based on real physics, not fantasy. In fact, time dilation isn't just a movie concept. It's something we measure every single day. So, is time dilation from Interstellar real? Or just an exaggerated Hollywood trick? Stay with me because the truth might bend your understanding of time and space. Time dilation is a phenomenon predicted by Albert Einstein's theory of relativity, both special and general. But what does it really mean? Let's simplify. Time doesn't tick at the same rate for everyone. It slows down for objects moving very fast or experiencing stronger gravity. Think of time as a stretchy fabric. Under certain conditions, like high speed or strong gravity, it stretches. And what we perceive as a minute might not be a minute for someone else. But hold on, is this actually measurable? Yes. It's proven, not once, but repeatedly. Let's take a particle called a muon, a radioactive particle formed when cosmic rays hit Earth's atmosphere. At rest, a muon has a lifetime of 2.2 microseconds. That's it. After that, it decays. Now here's where it gets wild. Physicists at CERN shoot muons near the speed of light in a particle accelerator. Guess what happens? Instead of decaying in 2.2 microseconds, they live for up to 60 microseconds, 27x longer. Why? Because at near light speeds, their time slows down. To them, their clock still ticks normally, but to us, they live longer. So here's the question. If we were on that particle, would we even notice, or would we age slower without realizing it? Time dilation doesn't just happen at high speeds, it also happens near massive objects, like black holes. This is where general relativity comes in. Einstein proposed that mass and energy bend the fabric of space-time, like a bowling ball on a trampoline. The more mass, the more it bends. And this curvature is what we feel as gravity. But there's a side effect. Where gravity is stronger, time ticks slower. Think about this. Clocks in GPS satellites, orbiting 20,000 kilometers above Earth, tick faster than clocks on the ground. Why? Because Earth's gravity is weaker up there. Engineers have to adjust for this time difference. Otherwise, your Google Maps would be off by kilometers within minutes. This isn't theory. This is real-world relativity in your pocket. Still think time dilation is fiction? Let's break down what's really happening when time slows near a black hole. And to do that, we need to bend something ourselves. Space-time. Imagine you're in space, far from any gravity. Space-time is flat. If light travels from point A to point B, let's say 600,000 kilometers, it takes exactly 2 seconds. Why? Because light travels at a constant speed of nearly 300,000 kilometers per second. Now place a massive planet between those same 2 points. Its gravity bends space-time, and light must now follow this longer curved path, about 1.2 million kilometers. Even though light's speed hasn't changed, it now takes 4 seconds to get from A to B. That means, from our perspective, time near the planet is ticking twice as slow, because every tick of the clock depends on how light moves through space-time. Where gravity bends space more, time flows less. So, in Interstellar, Miller's planet sits deep in the gravity well of Gargantua, a black hole millions of times heavier than our sun. Time is stretched to the extreme. 1 hour equals 7 years in orbit. Sounds wild, but it's based on equations from real physics, verified by Nobel-winning scientists like Kip Thorne. Let that sink in. The closer you are to intense gravity, the slower your time flows compared to the rest of the universe. Now let's dig deeper. If time is relative, what is now? Einstein once said, "The distinction between past, present, and future is only a stubbornly persistent illusion." 2 astronauts could disagree on what event happened first, and both be right. Even your brain distorts time based on emotions. A minute in fear feels like forever. An hour with a loved one feels like seconds. So is time just perception? Or is it a physical quantity we're just starting to understand? We've seen it in particles. We adjust for it in satellites. We simulate it in sci-fi. Yet it remains one of the most mysterious forces of our universe. Time dilation shows us one thing clearly. Time is not absolute. It's flexible, it bends, it stretches. And if we learn to master it, who knows what the future holds? So here's my question to you. If you could jump ahead 100 years by orbiting a black hole, would you do it? Even if everyone you know might be gone? Let me know in the comments. If you enjoyed unraveling the science behind Interstellar, smash that like button, subscribe for more science-backed deep dives, and remember, time waits for no one, unless you're near a black hole.